Hello. Today I'll be presenting incremental sequential rule mining with streaming input traces. We'll start by definition of data mining and its relevant subfields. Data mining is the process of extracting information from data, so separation of some interesting data from the rest. Temporal data mining is data mining that deals with data that is sequential. So sequential data is data that's ordered with respect to some index, for example, time, or as in the game of this chess, the index here is the move number between the two sides. The subfield of data mining we're looking at is pattern mining. Pattern mining deals with mining patterns as opposed to, for example, models. Pattern mining consists of item set mining, which deals with non-temporal data, and temporal and sequential pattern mining, which deals with temporal data. So subfields we are interested in are rule mining. So association rule mining mines rules of associations from non-temporal data, and sequential rule mining mines rules from temporal data. This is the subfield we'll be concerned with. So we'll be mining sequences. We'll be mining rules from sequences. So input is a database of sequences. Sequences are ordered list of item sets. So as you can see, here's the first sequence. The first item set is 1, 3. The second item set is 4, 9, and so on. Each item set, the items within it are unordered. So 1, 3 is the same as 3, 1. But each sequence contains item sets that are ordered with respect to each other. So whether 1, 3 came before 4, 9 or 4, 9 came before 1, 3 is important. Output is a set of sequential rules. Here's an example of a rule. X goes to Y. So this rule might be 3, 4, 9 goes to item set 7, 2, 6. The parameters we can specify for this algorithm, for the algorithms here, are support, which is the fraction of sequences that contain a rule, and confidence, number of sequences that start with X, but it doesn't matter, and with Y, right? So for example, this rule here, 3, 4, 9 goes to 7, 2, 6, is contained within the first sequence, right? So here is the 3, here is the 4, 9 in another item set. It goes to 7 followed by 2, 6. And in this case, this sequence doesn't contain this rule because 3 followed by 4, 9 or 9, 4, it doesn't matter. But then it's followed by 7. You can see here's the 7, but 7 is no longer followed by anything 2 and 6. 2, 6 precedes 7, but it does not follow it. This is because the order matters. And so you can see that, for example, the support of this rule is just one sequence out of 2, right? And the confidence is out of the sequences that start with this, how many end in that. So out of the sequences that start with 3, 4, 9, here's 3, 4, 9, 3, 4, 9, how many end in Y? Just one, so it's 1 out of 2. Partial ordered sequential rule mining removes this restriction on order of item sets within a sequence. So now this rule looks like, before we had angle brackets, right, like this, but now we replace this with a set. So a set of item sets 3, 4, 9 implies a set of item sets 7, 2, 6. So now the second sequence contains this rule as well. So 3, 4, 9 or 9, 4 is followed by 2, 6, 7. And the order of these things here between each other is irrelevant. What is relevant is that all the item sets within this rule come before all the item sets within this rule. So we couldn't have 7 happening before 3 and still say that that sequence contains that rule. So how does the data look and where do we get it? The data is of type of clickstream. So a user visits a bunch of links on a page, we record that interaction, and here's an example of how I can convert a clickstream to data. We collect links, we number them such that the same link corresponds to the same number. We separate the special characters by -1. We end the sequence with -2, and here's how our final sequence looks. Here's a file with a bunch of input sequences where different numbers represent different links. -1 represents separator and -2 end of line. We use 2 data sets of clickstream data. And the first algorithm that we'll be looking at is ERMiner. This is the algorithm that we extend. This is called equivalence class rule miner. So for this, we'll need to introduce a few notions, a few definitions. The first one is a left equivalence class. So given a particular item set W, right here, and an integer I, right here, we say left equivalence class on W of size I is the set of all frequent rules W, and frequent rules W goes to Y, and Y must be of size I. So it's all the rules the left-hand side of which is W, it's given, and the right-hand side of which is of size I. It doesn't matter what it is, as long as it has size I. It is I numbers long, I item sets long. Right equivalence class is similar. We are given W, and we're given I, and we say it's all the rules X go to W such that X is of size I, and W is given. Given these 2 definitions, we can define left merge. Left merge between 2 rules is just the item sets on the right being merged together, and right merge is things on the left being merged together. So the reason it's called right merge is because we're given W, right? And left merge, we're given the thing on the left, right? Here is an example of this algorithm, ERMiner. This is the notation we're going to use. We're going to say a rule X goes to W has these sequences that are supportive. So inside these square brackets, we're going to list 1, 2, 3, 4. These are the indexes of the sequences that contain this rule. And inside angle brackets, we're going to say these are the sequences that are confident. So these are the sequences that are that contain at least X of this rule. So here's an example of a database on the left. These are the set of sequences, right? The first item set is A, B. And on the right, we can generate rules of size 1 by 1. So left hand side of size 1 and right hand side of size 1. The requirement we make on this is that the support is half and confidence is also half. So let's look at this rule at the top right. We can see that A goes to B occurs in sequences 2 and 3. So if we look at sequence 2, here's A goes to B. And if we look at sequence 3, here's A goes to B. You can see that sequence 4 does not contain it, since there is no A. And sequence 1 does not contain it, since A and B don't occur as part of different item sets. You can't have a rule specify in inter-item set relation. So the confidence is 1, 2, 3, meaning that A, the left-hand side, occurs within sequences 1, 2, and 3. So here we have A, and A, but not in 4. So once we generate these one by one rules, we can proceed to create left equivalence classes of size 1, right? So clearly, all of these start with A, and the right-hand side of these is of size 1. So this is a left equivalence class of size 1. Then we're going to do a merge. So we're going to merge all the things that we can, and we're going also to merge supportive and confident sequences indexes, and then we can throw out things that don't meet our minimum support requirement. So you can see here that after the merge, this rule is only supportive by sequence number 2, and we need support of at least 0.5. So but this is only 1 out of 4, 0.25, so we can throw it out. So now we can see this is our new left equivalence class, which we can merge again. After we merge it, we can find another rule that doesn't meet minimum support requirement. We can throw it out, and we can attempt a final merge, and this final merge produces a rule that does not meet our minimum support requirement, so we can throw it out. Now we can no longer do any merges, and we're done. Then we do collection of rules. So we collect all frequent rules and throw out any rules that don't meet our minimum confidence requirements. Here's an example of a set of final rules. Let's take this rule as an example. We can see that the rule A goes to CF has supportive sequences of 1, 2, right? So it occurs within 1, A goes to CF, and 2, A goes to CF, but it's not supportive by 3 or 4. So it has A but not CF, and this one doesn't have A at all. But it is but sequences 1, 2, and 3 are confident in this rule, meaning that they start with A. So A, A, A. Okay, so our contribution is to extend the ERMiner to work on unbounded data. So unbounded data is data that doesn't have an end, or equivalently streaming data, or online data. So, for example, here is bounded data. It finishes after some time, and unbounded data does not finish. It keeps new events can potentially be added to it. So our algorithm is IERMiner, incremental equivalence class rule miner. And let's go through an example. Here is the same database of sequences, but in this case what we're doing is we're just going to add one event to the sequence number 3. So we're going to add event C to this sequence. So we're not changing anything else except just this. So we already have a set of rules that we mined before with the ERMiner. Now we are going to scan those rules and find anything that contains C, and we're going to update support and confidence. So in this case, we can see that the a new supportive sequence has been added. So now that C is here, there is a rule A goes to C that's present in sequence number 3. So we say that sequence 3 is supportive of this rule. We can update the equivalence classes. We can see that this rule in this equivalence class is updated with this index. Then we can remerge only with modified rules. So we'll remerge only with the rule AC. We can see that these rules are now updated in left equivalence class of size 2. And we can see that this rule has now become frequent. We no longer need to throw it out. When we remerge with only modified rules, we update our left equivalence class A of 3. And then we can merge again. And then after merging, our left equivalence class A4 contains a rule now, which it didn't before, which is frequent and satisfies minimum support and minimum confidence requirements. Now we're done and no more merges are possible. So we can see that these are, now we can update all the final rules, and we can see that these are the final rules, and this is the new rule. Everything in boxes is the thing that has been modified. So you can see out of a rule, the rule set that we mined before, only a few rules were modified after our algorithm was finished. So our implementation contains these components: rule generator, the thing that generates these initial rules, left equivalence class processor, right equivalence class processor, and an aggregator. How do we ensure that our implementation is correct? Well, we run it side by side with the original algorithm. So ERMiner and IERMiner are run by side, and we compare the outputs. So initially our database is empty. We don't run ERMiner, but we supply our algorithm with just indexes of the sequences that are to come. Now, as we add new events, let's say we add one event here, A, the ERMiner output is the whole database, so sequence 1A. But our input is only the index of the sequence and the event that was added to it. So for the next time when we add event AB to sequence 2, we resupply the whole database to the original algorithm. But for our case, we only need to take sequence index 2 and the event that was added. Let's go to later time steps. So in this case, you can see at the bottom left that our database is modified by adding event CEF to sequence 2. So the original algorithm receives the whole database again because it has to start from the beginning, versus our algorithm is only receiving what was added to sequence 2, so event CEF. We ran all our experiments on a relatively modest machine, and some of them took up to 3 days to complete. The results, here are some of the results. You can see that ERMiner, the original algorithm, predictably takes linearly longer, the more events that are added to the database. This is predictable because it has to restart from the beginning and remind the whole database. Our algorithm performs better because it is able to take advantage of the existing rules that are present in the rules set that we mined so far. Here are some more results for another experiment, and we can say again that our IERMiner is doing better and is not increasing as exponentially as ERMiner. And this is experiment number 13. And you can see these experiments in our paper. Performance is, conclusion is that the mean execution time of our algorithm is less than that of ERMiner, and the difference is statistically significant. For the future work, we would like to parallelize the algorithm, mine more than one event at a time, deal with out-of-order events. So if we edit event that arrives out of order, can we handle new dynamic sequences, right? Can we create new sequences in the database, not just events? And maybe we can make use of this pre-large concept from item set mining to improve our algorithm. So this is the end of our presentation. Thank you very much.